Good afternoon, everyone. Good morning, good evening to folks who are joining us from across the globe. Cloud tech has significantly changed the technology landscape over the last decade for small businesses and large enterprises alike. It has brought scalable computing power to anybody who has a cloud account. There is no restriction at all. You have the full power of the cloud with you. And architects love the cloud. We push to move all of your apps, all of your data centers into the cloud so that you could make good use of the power that the cloud offers until they stop working. And then we don't love them as much. In December last year, there was a major outage in one of the cloud providers. It took many apps that were tied with it when it went down. This is not an isolated incident to that particular cloud provider. Over the years, there has been many outages across the cloud vendors. And when the outage happens, it impacts different organizations in different ways. If you're a social media app, that is one thing. It doesn't work for a few hours, no big deal. If you're a bank, it's a completely different story. Imagine walking into a bank and they say, no money for you because our systems are down, whatever. Or if you try to use your credit card or your debit card from the bank and the bank says, nope, no money for you. Could be an airline. If your airline stops working, that's not going to be a pleasant day. As bad as these are, there are even worse scenarios. Try to think of a healthcare provider who has their critical systems tied to one cloud. And even more realistic scenarios would be a healthcare provider unknowingly being dependent on another system, which in turn depends on one cloud. Bottom line is, if your app is tied to one cloud, you will fail with the cloud. It is inevitable. Beyond the problem of failing with the cloud, by staying with one cloud, we are denied the opportunity to use the services that another cloud provider has. That is frankly better. So for many organizations, multi-cloud, multi-region has become a necessity. Multi-cloud provides us the resiliency that we need, and in addition, get the freedom of choice to use any services from any cloud vendor. So what is the problem? Multi-cloud, multi-region is a complex implementation. Many organizations stay away from it because of this complexity. But what if we could make the architecture simpler to accommodate multi-cloud, multi-region? Perhaps then many organizations would be willing to more easily go to this paradigm. Let's see how. My name is Sanjay Narendran. First name Sanjay, last name Narendran. I was born in Tamil Nadu, India. Actually, in Tamil Nadu, India, many of us don't really have true last names. The last name that you see there, that is my dad's name. As I was growing up, I realized that we have it this way because every form in the country and every name processing and name input systems in the country always had this format: first name, middle name, last name. And so we as a community collectively decided to use our dad's name in the last name section. We are not alone. There are other communities that don't have last names and they end up using their village names in the last name. Why? Because everybody's trying to conform to that first name, middle name, last name format, that particular blueprint. Why am I telling you this? You will know that by the end of this presentation. I live in St. Paul, Minneapolis now with my wife and my 3-year-old. I'm a solutions architect at Sunrise Banks. We are a technology-first bank with our headquarters in St. Paul, Minneapolis. Our primary mission is our community's financial wellness. We are a proud member of GABV. It's a global alliance for banking on values. We are also a certified B Corp. It is a recognition given to organizations whose leaders build communities, not just profit. We are very proud of that. This is also the prime directive for our IT organization. And so in today's presentation, we wanted to share with you, the global IT community, the principles, patterns, and the architecture that we have used to establish and scale our multi-cloud presence. At Sunrise Banks, we believe that if the implementation is complex, then the design is wrong. Is there a better design? And so we have developed an architecture pattern called symmetric architecture. Design apart, what we have used to implement that design is the HashiCorp Cloud platform. And that's about the only platform that is available today that's mature enough to handle things at this scale. You'll see how. Symmetric multi-cloud architecture works at 3 levels. Level 1, Level 2, Level 3. In Level 1, we try to establish symmetry across regions, across clouds. We do that by arranging our Vnets in a certain way and forcing communication to happen in a certain way that could be very easily replicable across regions. That gives you the symmetry across regions. In Level 2, not only are your regions and clouds symmetric, but individual Vnets within those regions or across regions, they also look the same. Now, Level 3, that is the highest level of symmetry that you could achieve, not only are your Vnets and Vpcs, whatever, look very similar to each other, the arrangement of subnets within those Vnets are also very similar to each other. Let's look at Level 1 first. So in a Level 1 system, we follow certain rules to simplify a lot of the setup that needs to be done. All our Vnets are set up with a /16 CIDR address space. All our Vnets are split based only on the second octet if you're using IP4 addressing. We do not piecemeal IP ranges. We do not combine IP ranges. If we run out of space on one Vnet, we simply create another Vnet, also with a /16 CIDR. If I think about why people piecemeal IP ranges or start combining IP ranges, I really think it's a carry forward from like the on-prem days where these are physical entities. In the cloud, these could be just entries in a table somewhere. That's all. So let's say we start with Azure US East and we want to create a Vnet. We start by creating a Vnet, and as you can see, it's 10.100, which is a /16. And now when we want to create another Vnet, those would simply be 10.101, 10.102, 103, and so on. We allocate slots of either 5 or 10 /16 IP spaces to each cloud, each region. And what we do is, if we don't end up using all of the IP ranges in that slot, we simply leave them as spare Vnets. So in this example, we allocated a slot of 10 /16 IP addresses. So our Vnets go from 10.100 to 101, 102, and then we don't need the rest, so we leave 103 to 109 as spares. That's the first thing. Once you arrange the Vnets in this way, the only way that they can communicate or should communicate to each other is using the vendor provided regional hubs. If you're using Azure, it'll be like the virtual hub. If you're using AWS, it'll be the transit gateway. But the pattern is that the only way that the Vnets could talk to each other using the virtual hub, or the transit gateway. Now, the virtual hub also serves as the conduit for communication with your on-prem data centers. This is the only way that communication flows from the data center to your Vnets. So you have the blueprint. Now let's say we want to create AWS. And I'm using Azure and AWS just to depict the architecture. It could be essentially any cloud. So we start by creating our AWS US East we follow the same pattern. We start by creating the first VNet. Notice the 10.110 because we allocated the 10/16 slots to Azure US East. We're starting with another /16, 10 slots of /16 on AWS US East 1. Start with 10.110. Then if you have more VNets, simply do 10.111, 10.112, and then leave the rest of your VNets as spared. Here again, the only way that they communicate to each other, those VNets, is through the vendor provided transit gateway. And now you can connect your hubs to other hubs within your cloud. This is a very simple pattern. It's the same pattern that we used for Azure. Use the same pattern for AWS. And you have set communication flows between the clouds and your data center. Now let's say you want to expand. You want to create Azure in US Central. You have the blueprint, take the blueprint and then apply, and you have another region. Same concept, same structure, everything looks symmetric. That is level 1 symmetry. We'll talk about level 2 symmetry next. In a level 2 symmetric system, not only are your VNets, the arrangement of VNets and the region itself being symmetric across clouds, the VNet itself, the structure of the VNet will be very similar to the structure of other VNets, either within the same region or across clouds. How does that work? So in this example, we have taken an Azure virtual network, and I'm going to split it into security zones. Just to keep it simple, I'm going to split it into 8 security zones because it's a 64K address range. You'd get about 8,000 IPs in each zone. And it looks like this. So zone 1, 2, 3, 4, 5 through 8. Zone 1 could be your proxy edge zone. Zone 2 could be web DMZ. Zone 3 could be app DMZ. Zone 4 is for data and then file stores, whatever. And we leave zone 5 through zone 8 as pairs for future use. And keep in mind, this is a logical subdivision. There is no physical subdivision within the cloud providers for a security zone. When we start to create another VNet, let's say we want to create this in AWS, we preserve the same structure for each of the zones. So AWS also has 1, 2, 3, 4, 5 through 8 zones. And then within that, we might end up using zone 1 through 4 for the same functions, the proxy, the web DMZ, app DMZ data, and then we leave the spare zones. You could divvy up this into as many zones as you want. The only thing is that it must be consistent across all of the VNets. And then whatever you do not use, leave them as pairs for future expansion. The key thing here is, even though you might split this as different IP address spaces, when I look at a zone in one VNet, I should always expect to find the same zone at the same IP in the other VNets or VPCs. So in this example, my proxy edge that starts at 10.100.0 for my Azure, I expect to find a 10.110.0 in AWS for the same zone. That should not change. This will give you a symmetry where all of your VNets will have the exact number of zones and all of them start at the same IP address on the third octet. Let's look at level 3 next. In a level 3 symmetric system, not only are the zones the same across VNets, but we identify and pre-create a standard set of subnets in those zones. And those will be also consistent across VNets. So in this example here, I'm showing you one subnet per zone. Doesn't have to be. So in like the data zone, we have a DB data A0 subnet. And I always expect to find a subnet with that name across other VNets or VPCs that are in my cloud presence. So here is AWS VPC, and I expect to find the same subnet in the same zone, irrespective of which region or which cloud. Same thing with AppDMZ. So I have a subnet called VMs, AppDMZ, subnet to host the VMs, and I expect to find the same subnet in AWS as well. Now, this doesn't mean that the number of workloads inside that particular subnet should be the same. In this example, the AWS VPC for that subnet has 45 VMs, and the one in Azure has 25 VMs. That's totally fine. The names and the subnets should be the same. The workloads inside them, number of workloads inside them is not expected to be the same. Now, I should mention about some cloud-specific nuances here, which we ran into and you will also run into. Some of the clouds require subnets to be created in each availability zone, not the zones that we had talked about. And some clouds do not have this constraint. So there needs to be some abstraction layer to get over this. It's fairly simple, as shown in the example here. You just create it with a slightly different name. But should be able to abstract that fairly in a simple manner. Now, for completeness of understanding, I wanted to put this picture out. I don't want everybody to think that we can create only one subnet in a specific zone. You can create as many subnets as you want in each zone. The idea is to just have it consistent across clouds. All right, so those were the three levels. Let's look at the advantages next. Just like our architecture, we wanted to design our implementation system in a way that does something similar to this. We want to create our multi-cloud presence. We should be able to say, hey, Terraform, here's my TFRs, create my data center in Azure. Oh, by the way, create one in AWS and GCP too. So how does the system work? For illustration, I'm going to show an example in AWS and in Azure. Again, it doesn't have to be, it could be any cloud. So when we create a TFVARS file, that TFVARS is cloud specific. We pass that to our Cloud Builder system, and the Cloud Builder system spins up the VPC subnets, the EC2s, databases, whatever. The Cloud Builder is cloud aware. It means that it knows that you are trying to create an AWS VPC versus an Azure Vnet. Now we take a different TFVARS file, this one for Azure, and pass it through the Cloud Builder system. It ends up creating an Azure Vnet and all of the resources within that. Now, because the architecture is symmetric, these two TFVARS files will be very symmetric to each other. They will have the same structure, same zones, same subnets. The VMs and stuff inside those subnets might vary, but the structure will be the same. So how does Cloud Builder work? We will see that next. So the Cloud Builder system takes in terraform.tfrs as input, and then it puts out an entire VPC or Vnet with all of the assets inside that. Let's peel back the layers. The system is composed of three separate layers. The first one, or what we call the primitive modules, primitive in like primitive data types. So we have modules that are published by Terraform that creates network subnets within AWS. In this example, I've shown AWS. There are Terraform modules that create networks in Azure. Similar concept, create Azure Vnets, Azure subnets. Like that, there are other modules that create, say, for example, VMs. So there's a VM module for AWS that creates an EC2 instance with a disk and a NIC. And then there is an Azure module that creates an Azure VM with a disk and a NIC. Now, typically in a Vnet or a VPC, there is obviously more than one VM. So we need an aggregator module that creates multiple copies of the VMs based on the configuration that you provide. That configuration is in your Terraform TFRs. It is usually in a JSON array with like the host name and other specifications for that VM. So the aggregator module reads that array and it calls the primitive modules one per VM. Beyond the process of aggregations, there may be situations where you would want to apply your organization-specific defaults before calling these primitive modules, and those are also done in what we call aggregator modules. So in this example, I've shown you like a network and then VMs, but it could be for databases, could be for blob stores, could be for any asset that is created within each cloud. You just have a running list of all the modules and all of the primitive modules as part of the Cloud Builder system. So that's all good. We need something to act as a traffic cop. So the Terraform.tfvars is a configuration for the entire Vnet or VPC and all of its assets. So the main module that we have here, that acts as a traffic cop. This is like a good manager. Doesn't do any work by itself, but ensures that it passes on the work to somebody else to get it done. And in this case, the main.tf simply reads through all of the TFR configuration and it says, oh, you want to create a AWS VPC. Let me call the AWS VPC aggregator module and I'll let it spin it up. And then it'll say, oh, you want to create VMs now in AWS. Let me call the aggregator module for VMs and I'll let it spin it up. So that's all it does. For whatever you have in the TFR's configuration, the main module ends up calling individual aggregator modules, which in turn calls the primitive modules that spin up your individual assets. And together, this system ends up taking in a TFRs and then putting out an entire VPC or Vnet with all of the assets within it. I'm going to show you some code here. It's not a lot, and it's by no means a complex system. On the right-hand side, bottom right, this is a standard module that's available in the Terraform registry. That is to create a Windows server within Azure. And I put the link there if you want to go and look. Now, above that is an example of how an aggregator code will function. The key thing there is the for each loop. So for each essentially is reading through your array of individual VMs and is calling the primitive module to have it created. The merge statement that you see there merges the defaults. Some people put the defaults within the primitives. We have chosen to provide that also in our TFRs config so that we could say, hey, you know, if anybody wants to create a VM and they don't know what VM they are asking for, create a VM with like 4 cores and 16 gigs. Okay, that's what the default is. Now to the left, where you have your main module, and that is essentially a traffic cop, does nothing. Simply calls the aggregator modules if it finds a configuration within your TFRs for that. So in this example, main says, hey, you have a config for an Azure VM. Let me call the aggregator module for Azure VM. The aggregator module in turn spins through all of the VMs that you have in your config and calls the primitive modules, which in turn creates your individual VMs within that Vnet. So this is all fine. This is for one Vnet, but as we started, our goal is not to just have one Vnet. Our goal is to have symmetric Vnets across clouds. So how do we do that? So we have one Vnet or VPC and we have an associated TFVAR file. And that's all great. At this point, when you start to scale, there are 3 important things that we need to think about. The first one is lifecycle management and CI/CD. The second one is module management, because the cloud builder is just a composition of modules. And the third one is how we manage our secrets across clouds. Let's talk about the first one, lifecycle management and CI/CD. So as part of the cloud creation process, we have to go through the lifecycle of Terraform plan and then validate and then do a Terraform apply. We started to build a CI/CD system ourselves using Git, and we realized that it was a lot of work. And then we found out that Terraform Cloud, so part of the HashiCorp Cloud platform, has a system of workspaces and lifecycle management already. And it has the integration with Git that solves our CI/CD problem. So today, when we want to make a change, say we want to add a VM, we make a change to TFRs, Git and Terraform Cloud will automatically recognize that a change has been made, and then it will automatically trigger the Terraform plan process. And the plan will end up saying, hey, sounds like you want to create a VM, or you're cool with it, do you want to approve? And when you provide the approval, at that point it does the Terraform apply and starts creating your assets. That's one. Second one, module management. So in most of the organizations, you'd always have a production and a non-prod region. And so when a change is needed for one of the modules, the Cloud Builder module itself, one of its associated aggregates or primitives, we need a way to manage those versions. With Terraform Cloud, we get a module registry where each time you make a change to a module, that versioning is tracked. And so in the example that I've shown here, because these are shared modules, you'd want to first try this out in non-prod, make sure that things are working, and then eventually you'd make the same change, or you'd propagate the change to production, where you'd start to refer the right module version. And that's all managed within Terraform Cloud's private registry. Now, it's the same logic for other clouds too. If you have Azure, if you have prod, non-prod in Azure, it's the same principle where you will refer the right module version that is managed within Terraform module registry as part of your code. Now, as you expand, each of these clouds will have a set of secrets to manage. We went down the path of using the individual cloud providers' secrets management system, but then we realized that they are dissimilar, and either we have to write a secrets management system on top of that, or use something that is cross-cloud compatible. And that was HashiCorp's Vault, which is cloud agnostic. And so irrespective of the cloud that you're trying to scale to, you can centrally manage all of your secrets within HashiCorp's Vault. And really, this is it. You have the logic to create a Vnet. You have the system that supports multiple Vnets to scale across. And you have the architecture that ensures that all of these Vnets appear very symmetrical to each other. Where does that leave us? This is my 3-year-old's name. It turns out that he doesn't have a last name either, so he gets my first name as his last name. And then years later, in the future, he will have a son or a daughter who will have his first name as their last name. Irrespective of what happens, the blueprint doesn't change. The blueprint will remain the same. Symmetric patterns and blueprints simplify and solve complex real-world problems. Symmetric cloud architecture solves the multi-cloud problem the same way. If you like the presentation, share it with your groups. Perhaps you will help an organization get to its multi-cloud, multi-region goal. I'm going to hang around in the chat section for questions. Otherwise, have a wonderful rest of your day, everyone. Thank you. Bye-bye.